Assalamualaikum warahmatullahi wabarakatuh. My name is NURUL and I'm from M3CS2301C. Today, I want to present about Apple M1 architecture. First of all, I will start from introduction. Apple M1 is an ARM-based system on a chip, SoC developed by Apple company, and it is introduced in 2020 as part of the Apple Silicon family. So, it has been 6 years since it has been introduced. Apple M1 functions in both of the Central Processing Unit (CPU) and Graphics Processing Unit (GPU) for Apple's Mac desktop, notebooks, as well as the iPad Pro and iPad Air. The release of the Apple M1 marked Apple's major transition in Macintosh processor architecture, it is moving from Intel processor to Apple Silicon, following earlier transition from Motorola 68000 to PowerPC, and later from PowerPC to Intel. At launch, Apple claimed that Apple M1 delivered the faster low-power CPU core and the best performance per watt in the industry. The Apple M1 also replaced and integrates the functionality of the Apple T2 chip, maintaining security-related systems such as Bridge OS and Set OS even during low-power states to manage encryption keys for features like Touch ID, File Vault, Mac OS Keychain, and firmware passwords. Additionally, it stores the device unique and group identifiers. The chip includes a 16-core neural engine capable of performing up to 11 trillion operations per second. Apple M1 is the first processor created by Apple company specifically for Mac computers, offering a major improvement in performance, energy efficiency, and system integration. It was created from the ground up to operate seamlessly with Mac OS, allowing the hardware and software to work together more effectively than ever before. The M1 chip is designed to meet the demands of Mac system where compact size and low power consumption are essential. As a system on a chip, SoC, it integrates multiple advanced components into a single unit, including CPU, GPU, and memory controller. The use of a unified memory architecture allows all components to share the same memory pool, significantly enhancing speed while reducing energy usage. Built using advanced 5nm manufacturing technology, the Apple M1 contains approximately 16 billion transistors, making it the most complex chip Apple has ever produced. It delivers industry-leading performance with its high-efficiency CPU cores, powerful integrated graphics, and an advanced neural engine that accelerates machine learning tasks. The Central Processing Unit (CPU), which powers the M1 chip, features 4 high-performance cores and 4 high-efficiency cores. While the high-performance cores are responsible for handling intensive tasks, high-efficiency cores are responsible for handling less intensive tasks, targeting overall power consumption. The Graphics Processing Unit (GPU), as part of the M1 chip, is intended to serve only graphics processing. Graphics processing is very essential for functionalities such as playing videos, editing photographs, and gaming. It is optimized to consume low power while providing powerful graphics processing. Furthermore, the Apple M1 chip comes equipped with a neural engine, which is specifically suited to handle machine learning tasks. The neural engine is capable of carrying up to 11 trillion calculations per second, which is quite efficient in performing AI-related tasks such as recognizing images and speech. The M1 processor has an 8-core CPU, an integrated GPU that supports up to 8 cores, and a 60-core neural engine. The Apple M1 processor concentrates on balancing performance and power consumption. The Apple M1 processor also has a process size of 5nm and combines many components into one processor. This processor contains the CPU, GPU, and memory. It is also employed in the MacBook Air computer, the 13-inch MacBook Pro computer, the Mac Mini computer, and 24-inch iMac computer. The processor can also be seen in the iPad Pro computer, giving the user desktop-level performance in the form of a tablet computer. The Apple M1 processors adopts a hybrid CPU design that includes 4 high-performance cores known as Firestorm and 4 power-efficient cores called iStorm, a configuration first introduced in the A14 Bionic chip. This architecture follows a concept similar to ARM's Big Little approach and Intel's Lake-filled processors, enabling more effective power management compared to earlier Mac systems that relied on Intel processors. According to Apple, the efficiency cores consume significantly less energy, requiring only a fraction of the power used by the performance cores. Apple M1 is equipped with an 8-core CPU made up of 4 performance-focused cores and 4 efficiency-focused cores. The high-performance cores are optimized for demanding, single-threaded workloads and deliver exceptional processing speed while maintaining energy efficiency. These cores are designed to handle intensive tasks such as high-resolution photo editing and software development, allowing applications to run considerably faster than on previous Mac models. When combined, all 4 performance cores provide a substantial improvement in multi-threaded processing capability. In contrast, the high-efficiency cores are designed to handle everyday computing activities with minimal power consumption. Despite their low energy usage, these cores are capable of delivering performance comparable to earlier dual-core MacBook Air systems. They are ideal for routine tasks such as web browsing and email, helping to significantly extend battery life. When all 8 cores operate together, the M1 delivers exceptional computational performance while maintaining industry-leading efficiency in terms of performance per watt. The Apple M1 processors include several general-purpose registers that temporarily store data such as operands, memory locations, and intermediate calculation results. These registers allow the CPU to execute arithmetic and logical instructions more efficiently by minimizing direct access to main memory. During instruction processing, required data is first transferred into the registers before being sent to the arithmetic logic unit (ALU) for computation, which significantly improves overall execution speed. The program counter (PC) is a dedicated register responsible for tracking the address of the next instruction to be retrieved from memory. After an instruction is fetched, the PC is automatically updated to point to the subsequent instruction in sequence. This continuous updating ensures that program instructions are executed in the correct order without interruption. Another essential register is the instruction register IR, which stores the instruction currently fetched from memory. The control unit reads the contents of the IR to decode the opcode and identify the type of operation that must be performed. Based on this decoding process, appropriate control signals are generated to manage the execution stage of the instruction cycle. In addition, the program status register (PSR), commonly known as the condition register, maintains a set of status flags that represent the results of recent arithmetic or logical operations. These flags, such as 0, carry, negative, and overflow, are crucial for enabling conditional branching and logical decision making. In the Apple M1 processor, the clock system produces a steady stream of timing signals known as clock cycles, which regulate when instructions are executed, data is transferred, and control signals are triggered. Each clock cycle represents a fixed time interval during which specific internal operations are carried out, ensuring that all components of the processor function in a coordinated manner. The clock architecture of the Apple M1 supports dynamic frequency scaling, allowing different sections of the chip to operate at variety of speeds depending on workload requirements. During intensive computational tasks, the high-performance CPU cores can increase their clock frequency to maximize processing capability. In contrast, the efficiency cores run at lower frequencies when handling lighter or background tasks, helping to minimize energy usage and improve overall power efficiency. The Apple M1 utilizes multiple clock domains, meaning that major components such as the CPU, GPU, neural engine, and memory controller operate on separate clock signals. This design enables each unit to achieve optimal performance independently. In traditional desktop and laptop computer design, system memory is physically separated from processing units such as the CPU and GPU and is accessed through dedicated system buses. Data communication in these architectures depends heavily on bus controllers and interrupt mechanisms, which can introduce delays during processing. Although technologies like direct memory access (DMA) help reduce CPU involvement, memory access latency remains a constraint due to hardware separation and the presence of multiple bus layers. In contrast, the Apple M1 adopts a fundamentally different design strategy. By integrating the CPU, GPU, memory controller, and input or output components within a single system on a chip (SoC), the need for external buses and frequent interrupt handling is greatly reduced. The Apple M1's Unified Memory Architecture (UMA) allows both the CPU and GPU to access the same shared memory space, directly enabling faster data exchange without system interruptions. The Apple M1 processor employs an asymmetric cache structure that is carefully designed to optimize both computational performance and power efficiency. Each of the 4 high-performance Firestorm cores is equipped with relatively large Level 1 caches consisting of a 192 KB instruction cache and a 128 KB data cache. These sizable L1 caches allow rapid access to frequently executed instruction and data, which is especially beneficial for performance-intensive tasks. In addition, for their L1 caches, the Firestorm cores share a large 12 MB Level 2 cache. This shared L2 cache helps reduce access delays to main memory, thereby improving execution speed for demanding workloads. On the other hand, the 4 energy-efficient iStorm cores are designed with smaller L1 caches and share a more modest 4 MB L2 cache, aligning with their role in handling lightweight and background processes with minimal power usage. At the system level, the Apple M1 integrates an 8 MB system level cache (SLC) that is shared among the CPU clusters and the GPU. This cache serves as an intermediary layer between the processing units and main memory, helping to decrease memory traffic to the unified memory system and enhancing overall data throughput. Unlike the inclusive last-level cache designs commonly found in Intel processors, the SLC in the Apple M1 is slightly non-inclusive as its capacity is smaller than the total size of the CPU L2 caches. This design choice indicates a focus on reducing cache duplication and lowering energy consumption rather than maintaining strict cache inclusivity. The graphic processing unit GPU integrated into the Apple M1 chip is created to efficiently manage graphics-heavy tasks such as video rendering, image processing, and gaming, while maintaining low power consumption. Apple developed a custom GPU architecture with up to 8 cores, although certain entry-level models are equipped with 7 cores. This GPU is specifically optimized to operate seamlessly with macOS applications and workflows. Each GPU core is organized into 16 execution units EU, and every execution unit contains 8 arithmetic logic units ALU. This architecture results in a maximum of 128 execution units and 1024 ALU, enabling the GPU to support tens of thousands of parallel threads simultaneously. The extensive parallelism allows the M1 GPU to efficiently handle complex graphical computations and highly parallel workloads. The Apple M1 GPU is capable of achieving peak single precision performance of up to 2.6 teraflops, placing it among the most powerful integrated graphics solution available in personal computers at the time of its introduction. The GPU shares both the system-level cache (SLC) and the Unified Memory Architecture (UMA) with the CPU. This shared access reduces memory access delays and enhances data exchange between processing units. As a result, the Apple M1 GPU can support smooth playback of multiple 4K video streams and perform real-time rendering of detailed 3-dimensional graphics while consuming relatively little power. This balance of performance and efficiency makes the GPU suitable for a wide range of tasks, from everyday multimedia usage to professional creative applications. Thank you for watching.